Welcome to live session 9. First thing I want to mention over here, whoever the attendees are for this session in this joining technologies for metals session, I request you guys to attend the live sessions. So these sessions will be beneficial for solving your assignments and not even assignments. I believe that these sessions will be beneficial for you only to understand different aspects related with metallurgy, related with welding, related with some other technical issues, right? So until and unless you are attending this session, uh, just watching the videos, just solving the problems, just solving in terms of multiple choice questions, uh, the concepts cannot be clear, right? So you should you should uh, you should talk with your instructor. You should discuss with your friends. You should yeah. So I believe that attending this session will be greatly helpful for you in future. In future, any kind of interview or any kind of job interview on those things. So please attend the classes, right? Otherwise, as an instructor, as an coordinator for this session, uh, it's going to be difficult for me also to record a session with not many students, right? So please attend the sessions. So in this session, this is live session 9. Um, what we will do today, we will be going through different strengthening mechanisms. So we have gone through different strengthening mechanisms earlier also. This session will be much more on discussing and understanding different aspects uh, related to related to weldability of metal structures, right? So we will go through this precipitation hardening again. We will go through transformation hardening. We will go through strain hardening, work hardening of metals. So you'll go through those uh, those parts one by one. So let us start quickly. As I was saying that metals can be strengthened in several ways, right? As you know. So I was talking about this solution hardening, work hardening, precipitation hardening, transformation hardening, right? Now, the effectiveness of these hardening mechanisms can be significantly reduced with heating during welding in the heat affected zone. So, first thing, my tablet is not working for today, so we will be using presentation mode only to whatever I will write it down, it will be in presentation mode, right? So I cannot do pen and paper today. Fine. So what I was saying is effectiveness, effectiveness of strengthening mechanism increases with uh, reduces with increase in temperature, right? That is a very well known thing. Now the peak temperature is in the heat affected zone. The peak temperature is too low to cause melting, right? Mm, you cannot observe melting in the heat affected zone. So heat affected zone is the subse the beside zone of the fusion zone, right? So you cannot see melting over there in the heat affected zone. However, the temperature is high enough to cause any change in your microstructure as well as in your property of the material. You know, so if you see when a metal is cold work, so I would say without any thermal effect, if your metal is cold worked and plastically deformed, for instance, let's say you are doing some cold rolling or extrusion, what will happen in terms of metallurgical aspect? There will be dislocation generation, right? So dislocation generation will be there during any kind of deformation process, right? Now this dislocation can interact with each other, right? If they interact with each other, they will form some kind of tangle. So we call it dislocation tangle. Okay. So if they interact with each other, they will form dislocation tangle. Now such dislocation tangles hinder the movement of new generated dislocations. Right. Now in this way, the metal is strengthened or hardened by cold work. So there will be lot of dislocations. They will interact with each other, and due to interaction of those dislocation, they will hinder the movement of new generation of dislocation, and they will hard the metals. Right? This is called work hardening. Now, most of the energy expanded in work hardening that appears in the form of heat only. Okay. So if you see in microstructure, a finite fraction of energy is stored in the material as strain energy. So strain energy is always stored, which is driving force for recrystallization, right? Now, this energy is called, whenever your recrystallization will occur, that energy which will be released. So my strain energy which will be stored, that will only release during the process called recrystallization. So this energy is released as fresh and strain free grains, right? So recrystallization is strain free grains form, right? Now if you see this extent of recrystallization, how will it vary? Extent of recrystallization increases with increase in annealing temperature and time. Okay, so if I plot, let's say I want to plot some graph. Okay, want to plot some graph. My x-axis is percentage elongation, so I will mention it as strain percentage. Okay, and this is my stored energy. So let's say this is energy. My y-axis is stored energy. So how will it vary? With increase in percentage elongation, my stored energy will get increased. So this is E, correct? Now, this work hardened metals, I was telling that the strength of a work hardened metal that tends to decrease with increase in annealing temperature and time. As simple as that. Okay. Now, there is another procedure called recovery. So before recrystallization, some kind of process takes place, which I was calling is at recovery. During that period of time, certain properties of work hardened material, for instance, let's say electrical resistivity, what will happen? that will tend to recover without causing any microstructural change. So you will not see any kind of change in your microstructure before recrystallization happens. Okay, and this is called recovery. So is surface energy. How grain growth occur? So you will have your total grain boundary area, and there will be some surface energy, total surface energy associated with your system, right? Now, the surface energy that will reduce if your grain size is getting increased. So with portioning of grains, my surface energy will be getting reduced, right? So it is something like this. Let's say this is my x-axis is duration of annealing. Let's say this is time, the annealing time. Okay. And this is annealing temperature. The y-axis is annealing temperature. Now, if you are increasing your temperature as well as time, you will be increasing your grain size, right? So something like this. I am increasing my grain size towards this direction. So as I go upward, this is my, let's say grain size is D1. This is my grain size D2. The grain diameter I'm talking about, right? This is my grain diameter as D3 and D4 and so on, right? So D1 will be greater than D2. That will be greater than D3. Okay. So that's how it happens. So we talked about recrystallization. We talked about grain growth. Now, will there be any effect of recrystallization and grain growth in fusion zone? So in fusion zone, you are going above your melting temperature, right? So because of melting, the wort hardening will be completely gone. And heat effector zone, that will be partially lost because of recrystallization and grain growth. So these strength losses should be taken into account when you will design something for your weld joint, right? So yeah, those things need to be taken into consideration during your design of weld joint. Now, if you see the thermal cycles, if you see the thermal cycles, let me take another new slide. If you see the thermal cycles, let's say this is my time and this is temperature. Okay, and this is my cross sectional view. So this is my weld zone. What is this? This is fusion zone, and this is my heat affected zone, right? So let's say I am taking 3 points. One is near this heat affected zone, one is point 2, one is point 3. So which one will experience the maximum temperature? Point 1, point 2, point 3. Of course, my point 1 will experience the maximum temperature, right? So if this is for point 1, point 2 will be experiencing somewhat little lower, and point 3 further lowest temperature, whatever I'm considering it right now. Now if you see, um, is there an eraser? This is the eraser. So this is my time and temperature plot. Now if you see the strength or hardness of a metal in these three different regions, how will it vary? So this is my distance from the weld center, okay? And this is my, let's say, sigma. Sigma I am denoting it as for strength or hardness, okay? So the loss of strength will be highest for the location 1, which is experiencing the maximum temperature, right? If you plot this variation in strength, this will be the lowest one, 1, 2, and as I go towards this base metal zone or that will be unaffected zone, right? So this is 2, this is 2, and this will be my location 3, correct? So closer to the fusion boundary, higher the peak temperature becomes, and longer the material stays above the effective recrystallization temperature, right? So close to fusion boundary, as I am moving close to fusion boundary, I should take red. As I am moving close to fusion boundary, my peak temperature will be higher, right? And higher the peak temperature, the time also will be higher for the material that will be experiencing the above recrystallization temperature, right? Now under rapid heating during welding process, recrystallization temperature may increase because recrystallization, what does it require? Recrystallization requires some kind of diffusion, and diffusion always takes time. So since your strength of a work hardened material decreases with increasing annealing temperature and time, the strength or hardness of your heat affected zone also decreases as you are approaching towards fusion bound. So my strength is reducing as my temperature, time above recrystallization temperature, I'm increasing the, right? Now, what will be the effect of welding parameters? What will be the effect of welding parameters? Both the size of heat affected zone and the retention time above your effective recrystallization temperature, that will increase with increase in heat input per unit length. What is heat input per unit length? So heat input per unit length, I'll be denoting this as Q by V. Q is my heat flux. This is my heat flux, and this is my welding speed, right? The ratio of total heat input to the welding speed, that is known as heat input per unit length. So as you will be increasing your heat input per unit length, I will be increasing my size of heat affected zone, I will be increasing the retention time above the effective recrystallization temperature. So consequently, what will happen? There will be loss of strength in your heat affected zone because more severe as the heat input per unit length is getting increased, right? That the effect will be more severe. Correct? Now, if I want to plot this grain size, how will it vary? If I want to plot this grain size, how will it vary? So this is my distance. This was my distance. The x-axis is my distance. Correct? And let's say this is my grain diameter or grain size. So which location will experience the maximum grain size? The location which is experiencing more temperature and time above recrystallization temperature. As simple as that. So my location 1 will experience the highest grain size compared to grain location 2 and location 3. As you are approaching towards the base metal region, I will end up with some uh, much finer or much unaffected region, right? As you are increasing time and temperature, you are enhancing something called grain coarsening. Correct? I was talking about this heat input per unit length. I was talking about this heat input per unit length. So uh, let's say this is my fusion zone and this is my heat effective zone. For other condition, this is my fusion zone and this is my heat affected zone. For the next one, this is my fusion zone, this is my heat affected zone. Fine. And let's say this is the center line. What is this? This is my weld center line. Okay. Now, this is location 1 in the heat affected zone. This is location 2 in the heat affected zone. And this is location 3 in the heat affected zone. So as I am moving downwards, what is happening? I am increasing my heat input per unit length. Q by V is getting increased. And as I was saying, as you are increasing your Q by V, the ratio of total heat input to the welding speed, your size of the heat affected zone will get on increased, right? So how my strength will vary then? So let's say this is, and to plot my strength plot at location 1, location 2, and location 3. So if this is my location 1, this is my location 1. This is for location 2, and this is for location 3. This is strength. Correct? This is what we are talking about. Any question? Now, can you tell me, in electron beam welding, will you see more amount of recrystallization or less amount of recrystallization? What happened in electron beam welding? Electron beam welding. In electron beam welding, it offers low heat input, right? You will have low heat input and cooling rate is higher. Cooling rate is very high in electron beam welding. So very little recrystallization is observed in the heat affected zone of your work hardened material. On the other hand, if you consider gas tungsten arc welding, if you consider gas tungsten arc welding, how can you characterize a gas tungsten arc welding process? There you will have higher heat input and lower cooling rate, right? Heat input is higher and cooling rate is lower. Because of that, you are getting time for diffusion to happen. Decrystallization and even some grain growth will be observed in your heat affected zone. Correct? So I will come back to my original presentation. So we have talked about this recrystallization, work hardening, grain growth, right? Any question? What are some work hardenable metals? Can you tell me some work hardenable metals? Let's say you are considering aluminum alloy. Okay. So we are considering aluminum alloy, which is work hardened, and let us assume that is made either by a fusion welding or solid state joining process, whatever you feel comfortable with. Now, if the raised temperature of your base metal is high enough, that will show you significant softening, right? Your strength will be go down. Now, the heat affected zone softening mainly occurs due to 2 points. One is this loss of work hardening effect caused by this recovery process. I was talking about this recovery. The next is grain coarsening, right? And the degree of this softening and width of this softened heat affected zone, those mainly depend on your net heat input imparted during your welding process, right? These things we just discussed. So I'm basically summarizing whatever I'm discussing, whatever I have discussed till now. Now this recovery and this grain coarsening phenomena in heat affected zone, that will get decrease if you are moving away from your fusion boundary, correct? And by hardness will increase gradually until this unaffected base metal. We have plotted this. We have plotted this graph for better understanding, for better visualization, correct? And these variations in your structure, in your hardness of heat affected zone, why those will occur? Because you will be experiencing different thermal cycle during your welding or joining. I'll be experiencing different temperature at different location. The zone close to your fusion boundary that will experience higher peak temperature for longer time, which in so that will cause more severe recovery, recrystallization, grain growth phenomena. While on if you are moving away from your fusion boundary, uh, or the nugget, whatever you are forming in your, let's say you are doing fusion, And if you're moving away from your fusion boundary and going towards base metal zone, both peak temperature and this retention period, that will decrease, and that will cause lesser recovery, recrystallization, and grain growth phenomena. As simple as that, right? Okay, okay. So what we will do next, we'll talk about precipitation hardening. Okay, so we'll talk about precipitation hardening. So if you are thinking of precipitation hardened metals, aluminum alloys are most frequently welded uh, metals which can be strengthened by this precipitation hardening, right? Um, in general, high strength aluminum alloys are more susceptible to this hot cracking, then loss of strength, or loss of strength or ductility in your heat affected zone. Now, yeah, now let us discuss a little on this background of precipitation hardening. We probably have talked regarding this precipitation hardening mechanism of precipitation hardening. How does it work? Let us talk it again. So, aluminum and copper alloys, Al copper alloy. So, aluminum and Al2CO. Sorry, my recording got interrupted in between, but fine. So, what is the necessary criteria for precipitation hardening to happen? So my solubility of copper in the alpha phase, that should be increasing with increasing temperature, right? So solubility is very difficult to control this mouse, right? Solubility of copper increase with increase in temperature. Let's take example for aluminium 4% copper. So what you will do for alloying, what I will do, I will be initially doing some solution heat treating, right? I will heat the alloy in the alpha phase temperature range until it becomes some solid solution. So initially I will be forming solid solution. What I will do after that I will do quenching. Once I have done this solid solution generation of or development of the solid solution, I will do quenching to rapidly cool the solid solution to room temperature. When I am doing this quenching operation, when I am doing this rapid cooling thing, what it will do? It will super saturate the solution. My solution will be super saturated in copper. So the concentration of copper will be much higher, right? What it should be. So this will form a super saturated solution. Super saturated solution. Meaning, for some reason, this recording is not working properly. Okay. So I have made this super saturated solution. What my next step will be? My next step will be aging process. I'll be doing aging, right? So I'll be aging by heating at some intermediary temperature, let's say 190, which is called artificial aging also. If you're not heating the alloy material, then it is called natural aging. So there are two different aging heat treatment. One is natural aging, one is artificial aging. So there will be five sequential structures that will be identified during this artificial aging of aluminum copper. What are those? So initially I will be starting with this super saturated solid solution. And then I will be forming this GP zone. After that, there will be formation of theta double dash, then theta dash, then this theta phase. What are these? So my theta is the equilibrium phase. Theta is the equilibrium phase. Okay. What kind of structure does it have? Theta. So theta, this Al2C phase is having BCT structure, body center tetragonal. Remember that. Now the GP zones, sometimes called GP1 also. The theta double dash phase, that's sometimes called GP2, and the theta dash phase. These three. These three phases, they are metastable phases. They are not the phases that will form in equilibrium condition. Okay. Now these GP zones are coherent with crystal lattice of your alpha solid solution. That is fine. Uh, because the copper atom, you are mixing copper atom with aluminum, right? Because copper atom is smaller than your aluminum atom in diameter, and your GP zones, those are super saturated, right? Those zones are richer in copper than the solid solution. Then what will happen? Whatever your crystal lattice is having, the crystal lattice will be strained around your GP zone. If it is strained around this GP zones, the strain fields associated with these GP zones, they allow them to be detected in your electron microscopy. So you can detect these metastable phases after aging happens. This theta double dash, theta dash, those are also coherent, right? Uh, Theta dash actually semi-coherent with your lattice of your solid solution, is not related to the GP zones or the theta double dash phases. Now, if you see the maximum strength and hardness, when it will happen? So my maximum hardness or strain that will occur when the amount of theta double dash or GP2 region is at maximum. Some contribution may also be provided your theta dash, but maximum will happen when this is for theta double dash, right? So it will look something like this. This is my aging time. This is my aging time. Okay. So the unit of aging time can be in days. And this is, let's say, HV. What is HV? HV is Vickers hardness number. Correct? Now, what I will be plotting, of course, this whatever I will be plotting right now, that have been found out from experimental observation, right? So I'll be plotting two different temperature of aging. One will be at 190, one will be at 130. And there will be difference observed in your hardness value for this GP region, theta double dash theta regions, right? So one is this, which had been aged at 190 degree, where somewhere around aging time of 10 days, formation of theta dash was there, and towards the end, I'll be forming this equilibrium phase. And another temperature region is lower than this. So that will observe some characteristics like this. This is at much lower temperature. That was done at 130 degrees. So this is my GP1 region. Over here, this is my GP2 region. And subsequently, it will be forming the equilibrium phase. Correct? Any question? I will show you another graph. So what I will show over there, what I will show over there is the precipitation hardening curves of this aluminum alloy. This again also has been experimentally observed. So the alloy was naturally aged at room temperature, right? Before heat treating. So how will it vary? The initial strength decreases due to this dissolution of the GP zones that formed in natural aging. And as we'll be increasing the temperature, the faster overaging occurs and the strength gets decreased, right? So let's say this was the duration in hour. The maximum was somewhere around order of 10 to the power 4. Okay. And this is my tensile strength, sigma tensile. Fine. So with increase in duration, The lowest one will be at highest temperature. So this was aged at 260 degrees C. So this was aged at 260 degrees C. And as you will be decreasing your temperature, it will be varying something like this. So this was somewhere around 230. This was somewhere around 205. This was somewhere around 170 and so on, right? So what you will be seeing, the alloy had been naturally aged at room temperature before heat treatment, and the initial strength that decreases due to this dissolution of GP zones that formed in natural aging, and higher the temperature, the faster overaging will occur and the strength decreases, right? So higher the temperature. Suresh, can you please mute yourself? Higher the temperature, faster will be overaging, and strength decreases. Now, how will he characterize this heat affected zone of base metal that will be strengthened by precipitation hardening? How we will be characterizing that? So, to understand the heat affected zone characteristics of a precipitation hardened metals, we need to be aware of the stability of those precipitates, right? Those will be as which will be associated with the metal as a function of temperature. The stability of those precipitates is very important to understand the characteristics of heat affected zone. Now, the precipitates, whatever it will be forming, the strengthening precipitates, those get destabilized or dissolved in the matrix above certain critical temperature, depending upon depending upon the composition, right? Those will be dissolved with increase in temperature. There will be certain temperature above which you will see there is no precipitation formed. So there will be this reversion or dissolution of those precipitates. Now, formation and dissolution of those precipitates, those affect always hardness and strength of your metal during welding. So there are different uh, precipitation strengthened base metals, right? So if you see this aluminum series, there is this AA 2000 series. So we denote it something like this. This is aluminum 2000 series, aluminum 6000 series, aluminum 7000 series. These are some of the precipitation hardened metals, and they can be developed either by fusion welding or solid state joining process if you are raising a temperature of your base metal high enough. Now, over here, the heat affected zone, the strengthening of your heat affected zone that will occur due to two different process. What are those? There will be loss of strengthening precipitates, right? So there will be loss of strengthening precipitates due to dissolution. This is one. So I'll mention it as A. What is the other? The coarsening of grain precipitates. With increase in distance from fusion. So with increase in distance from fusion boundary, what will happen? Dissolution of precipitate decreases. And hardness increases as we approach towards this meter. Okay. So if we try to plot this effect of heating temperature, effect of heating temperature, so this will be my heating temperature. So this will be my temperature. X-axis is temperature. And let's say this is my joint characteristics. Okay. So I would say it's as joint, joint characteristics. So I'll be plotting two different graphs. One is residual stress. So my residual stress will be getting reduced with increase in temperature. This is for residual stress. What about the strength? So whenever you will be doing this recrystallization, my strength will get decreased, right? With increase in temperature, my hardness will get decreased and I will be increasing the ductility. So this is ductility. This is right? So the zone which will be close to your fusion boundary or weld nugget, that will be experiencing higher temperature, as simple as that. That will be experiencing higher temperature for longer time, and that will cause more severe reversion and grain growth, right? And as you go away from this fusion boundary in the heat affected zone, both the peak temperature and the high temperature retention period, that will decrease, and that cause lesser and lesser reversion and grain growth, that will lead me to some gradually increasing hardness of heat affected zone as you are going away from your fusion boundary, right? Now if you have some combination of decrease in reversion, so you have increased this availability of hardening precipitates, and as well you have somehow ended up with some finer grains and precipitates in a heat affected zone. What that will do, that will increase my hardness at the location away from your fusion boundary, right? So softening in heat affected zone, they always make it prone to fracture, right? So softening always are prone to fracture. I mention it as softening always are prone to fracture in heat affected region. Fine. And finally, we will be discussing on this heat affected zone of transformation hardened metal, how it will vary my weldability of the structure. And before that, what we will try to do, let us try first few, so try to solve few questions first. And then we'll move to this transformation hardened metals. So my first question tells me the regions which are closer to the fusion boundary in precipitation hardened alloy, that will experience what? So if you are more towards, this is fusion boundary, right? And this is heat affected region. As you are more towards closer to your fusion boundary, you will have lower temperature, lower retention period, or higher temperature, higher retention period, or higher temperature, lower retention period, or lower temperature, higher retention period. So we have discussed right now. So more towards fusion boundary, we will having higher temperature and higher retention period. Retention period means time for which it is staying there above some critical temperature. Let's say if you are thinking of recrystallization temperature, if you are staying above your recrystallization temperature, so that is retention period above my recrystallization temperature, that will be higher. Correct? Any confusion? Next question asks me, a zone which shows lowest hardness during friction stir welding of precipitate hardened metal is, which one will be the lowest hardness? So as you move away from your fusion boundary, so let's say this is my fusion boundary and this is my base metal. I'm moving away from fusion boundary. Over here, my strength will be highest, and I am sacrificing my strength and hardness regions near this fusion boundary. So which zone will be showing the lowest hardness during friction stir welding? So whatever mechanism I'm talking about, this is similar for friction stir welding, similar for fusion welding, because that depends on your thermal cycle, right? What temperature your metal is experiencing. So the weld zone will be the lowest hardness during friction stir welding of precipitate hardened metal, and as you are moving away from your weld zone, that will be increased, right? Next, we talked about this precipitation hardening of aluminum alloy right now. So theta phase formed in the final stage of aluminum copper supersaturated solution that will have crystal structure of what? This theta phase will be having a BCT structure. So I talked now supersaturated solid solution, supersaturated. From there you will be forming GP zone, then you will be forming this theta double dash, then you will be forming theta dash, and finally theta is your equilibrium. So this is BCT structure. The other crystal lattice structure can be coherent or semi-coherent with your structure for this solid solution. Fine. Next, dispersion strengthening. Any idea of what is dispersion strengthening? What is dispersion strengthening? This is also a strengthening mechanism, right? That will be enhancing your mechanical properties of materials. So it involves the distribution of fine stable particles. It can be oxides, it can be other compounds. So there will be a matrix material to form some metal matrix composite, right? So there will be a matrix material where I will be distributing fine stable particles. What those particles will do? The particles will hinder the movement of those dislocations. Dislocations are basically defect, right? So if you are hindering the movement of dislocation as you are progress with deformation, that will be strengthening my metals. Correct? So fine particles, uh, let me, fine, I will note it down over here. Dispersion strengthening. So I will be having fine particles which will be distributed uniformly. Those will be creating obstacles to dislocation movement that will be increasing my strength and hardness. As simple as that. Right? Now, common materials that can be dispersion strengthened. What are common materials? That can include aluminum, that can include titanium, some uh, steel materials also, like stainless steel, also can be dispersion hardened. So people have done this metal matrix composite, and these dispersoids, you call it dispersoid. So Al2O3, aluminum oxide can be a particle, silicon carbide a particle. Mostly oxidized and carbides, oxides, carbides are used as this distribution of those particles, right? Particularly, they are useful in high temperature applications where materials must maintain their strength under extreme condition. And how they can form? We can form it powder metallurgy. We can form it this friction stir processing. You can do these solid state kind of techniques or this dispersion strengthening. Now, this question asks me dispersion strengthened metals are susceptible to defect formation during fusion welding due to is it thermal damage to reinforcing agents? If you are doing fusion welding, so you are going beyond the melting temperature. Possibly you are not going towards the melting temperature of these particles. So these particles are always having much higher melting temperature compared to the base metal, right? If you are mixing Al2O3 or SiC with aluminium, aluminium is having some melting temperature around 660. What SiC melting temperature is? This is above 1000. So it may happen you are not going beyond melting temperature of those particles, but because of increase in temperature, you will be thermally damaging those reinforced agents. There can be wettability, change in wettability also. The viscosity of the melt will be changing. It will increase, enhance your viscosity. So it may happen there will be poor wettability also, right? So all of this is the correct option over here. Okay. The type of steel commonly used in thermal power plant is chromium model steel. Just remember that. I'm not going to explain that. So yeah, we are midway. So let us now move to this transformation hardened metals. Okay. So next we'll be talking about heat affected zone in the heat affected zone is transformation hardening. What are different transformation hardened metals? You can have steel, you can have cast iron, those will experience more complex changes than what we'll experience in work hardening and precipitation hardening metal during welding. So there will be change in your microstructure, change in your properties in heat affected zone of transformation hardened metals. So to understand this transformation hardening, understanding the iron carbon phase diagram, understanding this CCT diagram, continuous cooling transformation diagram is very important. I'll be not going into that direction, but those things will be the fundamental to understand this transformation hardening, right? Because transformation hardening is based on change in your phase, change in your microstructure, transformation of austenite into martensite, austenite into pearlite, formation of different phases, right? Now, if you see the weld thermal cycle that will be imposed during welding and that will be imposed during conventional heat treatment of steel, that is completely different, right? That is completely different. I mean, in during welding, you are going beyond melting temperature of steel. What is melting temperature of steel? This is above 1500. While you will be doing heat treatment, you don't go beyond this A1 or A3 critical upper critical temperature for austenite formation, right? That is somewhere around 900 degrees. So the weld thermal cycle experienced during this welding and during this heat treatment process is completely different. So the peak temperature in the vicinity of this fusion boundary always will be very high. So you have talked about well enough. And then they will keep on decreasing if you're moving away from your fusion boundary towards the unaffected metal. Now, in case of iron carbon system, based on your peak temperature experienced by heat affected zone, there will be 5 different zones can exist. I can end up with 5 different regions. What are those 5 different regions? So let me introduce you to these 5 different regions. So let's say this was my cross section. This was my fusion zone, correct? Then we will be having PMZ. What is PMZ? PMZ is partially melted zone. Then you will be having coarse grained heat affected zone. Then you will be having fine grained heat affected zone. Then you will be having recrystallization. And finally, you will be having this base metal. So I am having 5 distinct regions. So what will be the temperature that will be, or the range of temperature for these different regions? So if you see iron carbon phase diagram, if I am right, let me try to draw this iron carbon phase diagram initially. So what is this x-axis? This is carbon percentage, correct? And this is temperature. Over here, so one is eutectic, one is eutectoid. So I'm not explaining everything over here. I will just mention the main or critical phases. So this is somewhere around 1600, somewhere around 1500 probably, 1600. And this is somewhere around 1500. This temperature, this is around 700, and the upper critical is 900, right? And the dissolution can be at somewhere around 300 or 400. Fine. Now, This temperature is 730. This temperature is around 1100. Fine. Now, over this region, you will be having ferrite plus perlite. And over this region, you will be having ferrite plus cementine, right? I'll be having ferrite plus cementine. Over here, I will be having austenite plus cementine. And over here, I will be having ferrite plus austenite. Correct? What it will form over here? Over here, it will form austenite. This is all liquid. This is liquid plus cementine. And this is liquid plus austenite. Correct? Now, next to the fusion boundary, which is having temperature between this liquidus and solidus, as you know, that will form a mushy zone. So, the mushy zone is consisting of this delta ferrite or austenite and the molten metal in this region. Correct? So, this zone is called partially melting zone. So, for partially melting zone, the temperature range is somewhere around 1600 to 1400. For partially melted zone, my temperature range is 1600 to 1400. Okay. Now, this gamma region, gamma austenite, high temperature gamma region, which is forming only coarse austenite. And if you are having coarse austenite, it will be promoting formation of coarse martensite or pearlite as per cooling condition. So that region is called coarse grained heat affected zone. Okay. So coarse grained heat affected zone is for temperature range of 1300 to 1000. Fine. What next? Next is this fine grained heat affected zone. So the critical temperature zone that forms both austenite and ferrite, that will lead me to formation of fine grained ferrite, perlite or benite as per cooling condition. So fine grained heat affected zone temperature range is 900 to 700. And when my recrystallization will start? my recrystallization will start above 400, and that may continue till 600. So recrystallized structure is 400 to 600. Fine. So the zone that will be experiencing temperature between this subcritical temperature and recrystallization temperature, there my phase will remain unaffected, but the recrystallization will take place. Right? Now, if you are thinking with respect to retention period or soaking time, so the high temperature retention period during welding in heat affected zone is very short to develop homogeneous solid solution of austenite, right? Through complete dissolution and phase transformation, especially in alloy steel having some stable phase compounds. So what will happen? Very inhomogeneous solid solution of austenite will form uh, along with other stable phases that will be forming in heat affected zone. That will affect my transformation behavior of austenite. Correct? So yeah. So what I was talking about, high temperature retention period during welding is very short. Because that is very short, it cannot develop homogeneous solid solution of austenite through complete dissolution. So what it will do, it will form inhomogeneous solid solution of austenite. So it will form inhomogeneous solid solution of, that is the basic idea. So if you are increase in soaking temperature, that will decrease my time. Now the heat affected zone uh, that will be rich in alloying elements, right? Now if it is rich in alloy elements, that will lead to austenite to martensite transformation. While the regions that will be deficient of alloying elements, that will result in softer phases like ferrite, like pearlite or benite. So the region which is next to your fusion boundary, that will experience very high temperature for a very short period. And because of that, that will lead me to coarsening of grain for formation of usually inhomogeneous austenite, right? So if I draw some schematic, if I draw some schematic, so this is my soaking time and this is my soaking temperature, right? So over here, this will be pearlite, ferrite, cementite, austenite, not austenite over here. So this is in the temperature range of 900 to 700 I'm talking about. Fine. Now, as you are increasing your soaking time, I will be forming austenite, more austenite formation, ferrite formation, carbide formation, not carbide, cementile formation. This is somewhere range of 1000, let's say. Now, as you are going beyond 1000, let's say at temperature of 1200, and you apply more time, I will be forming homogeneous austenite all over, right? Now, my cooling rate will also affect, like peak temperature, the cooling rate that will be experienced by heat affected zone, that will be maximum also at fusion boundary, and then it keeps on decreasing gradually on moving away from your fusion boundary towards this unaffected base metal. So this coarser austenite in the heat affected zone, which I mentioned it as uh, coarse grained heat affected zone, that will tend to form martensite, while austenite in the fine grained region, that may form fine pearlite along with this uh, some pre-existing protracted ferrite structure, right? So in a very narrow region next to the fusion boundary, there will be large variation in your microstructural and mechanical properties that can be observed. So yeah, so you can ideally understand this from this CCC diagram, right? This cooling transformation diagram. Now let me try to draw it. Let me try to draw it. So this will be temperature, and what is this? This is time, correct? Now this is some temperature range where martensite will form. This is the temperature range where austenite will form, and then you will have this eutectoid temperature over here. I believe you have gone through all these things in your metallurgy courses probably. So this is my eutectoid temperature. Now there are different regions, right? To be particular, there are different regions. So this section over here, it will form austenite plus pearlite depending on your cooling rate. Now, if your cooling rate is much slower, something like this, it will form coarse pearlite. If your cooling rate is comparatively higher, like this, you will form fine pearlite. Correct? Then more increase in cooling rate, like this. Over here, you will form austenite plus pearlite, and over here, if you are going temperature below this martensite, it can form pearlite plus martensite. It all depends on time and temperature for which my material is experiencing. And over here, if you don't cross this region, If you don't cross this region, then this is much higher cooling rate, and that will directly convert in my austenite structure to martensite, which is hard and brittle enough. Right? Okay. So finally, we'll just go through this questions. I believe that that is enough for this in terms of explanation of different aspects of this weldability of structures associated with precipitation hardened, work hardened, transformation hardened metals. Let's finish this session by going through the remaining questions, right? So the main metal strengthening mechanism which will lead me to high strength in hardenable ferrous alloys. So this is hardenable ferrous alloys. Whenever you talk about ferrous alloys, we talk about precipitation hardening. Okay. Toughness of carbon steel with increase of carbon percentage. If you are increasing your carbon percentage, you will decrease your toughness. I have to arrange the following strengthening mechanism in the increasing order of their strength and hardness. So the maximum hardness will be for transformation hardening, then strain, then grain, then solid solution. So C is the correct option. Okay. And finally, the fusion based welding process which results in finest dendrites in weld metal, because this gas tungsten, gas metal, gas welding, they will increase your heat input. Cooling rate will also decrease, right? So they will not form fine dendrite formation. They will form coarse microstructure in comparison to laser welding. So laser welding will provide me the finest dendrites. Okay. So as I mentioned in the very early of this session, please try to attend the session in live so that that will be beneficial for me also, for my betterment in teaching. That will be beneficial for you also, right? So please try to attend the sessions. Otherwise, this will be only going through those MCQ, only just watching videos. That will not help you really. Okay, fine. So, okay. If there are any question, please ask. Otherwise, we'll finish this over here. So if there is no question, we'll finish the session over here. Okay. Bye bye.